Okay, I'll get started because I'm just mainly going to be writing out a table at the beginning. So to review what we had last time, here is a table of Laplace transforms. And there's going to be some redundancy on this table. So here is, if we have a function f, its Laplace transform is L of f. And then I don't know how long to make the dividing bar in the middle. So the first example that we did is if we have the function 1, its transform is 1 over s. And then there are two different generalizations of this. If we have the function t to the n, for n is a natural number, then we have the transform n factorial divided by s to the n plus 1. And in particular, 1 is the n equals 0 case of this. But also, if we have e to the at, then this transform is 1 over s minus a. And 1 is, again, the a equals 0 case of this. So this is a special case of both of these. Then we had, if we had, for example, sine of at, sine was the one that was nicer. So we had a over s squared plus a squared. And for cosine, we got s over s squared plus a squared. And then we had some rules that were pretty general. And what the general rules say are that if you're taking the Laplace transform of the nth derivative of some function, then what that's equal to is the Laplace s to the n times the Laplace transform of f. And then you go in decreasing orders of s n minus 1. And then you multiply it by f 0. Then you do s to the n minus 2, if that exists. F prime of 0, all the way down to f to the n minus 1 of 0. Then if we have some power of t to the n times f, well, this requires calculating a higher order derivative, and so it's a bit annoying. This is the rule that has a -1 to the nth power. dn dsn of the Laplace transform of f. And then if we have e to the at of f, then the Laplace transform is just a shift. It's the Laplace transform of f at s minus a. This is evaluation, not multiplication. And so those are our rules. And we're going to cover one more rule just at the end of today. So last time we did some examples. And just to go back to those examples, we, for example, found that suppose we had this equation. Suppose that y is a solution Okay, third time's the charm. Still missing a line, but whatever, I can fill that in. So last time, and the solution was just to copy what we had last time, that L of y was s squared over s plus 1 times s squared plus 2s plus 5. So now we can go further and we can solve this differential equation. So now we can find y. And what we have is that we're going to consider this expression s squared and this expression right here, we can complete the square. And if we complete the square, what do we get?
S plus 1 squared plus 4.
Good. Yeah. And so how we're going to do partial fractions is actually maybe a tiny bit different than how you did partial fractions in calculus, although I think that when I was doing calculus B, I also taught partial fractions in this way. And that's we're going to, well, for s plus 1, we know what the thing is. It's going to be a over s plus 1. And then for this term, it's going to be a bit more interesting. So the denominator is s plus 1 squared plus 4. And the numerator is going to be, well, you usually write as plus b, but I'm going to write as plus 1. Because we're going to want to do this shift anyway. So it would be more helpful to split it as as plus 1 plus b. Because we know how to inverse Laplace transform each one of these terms. So this is better. Well, so if that's the case, then I'm going to have that basically s squared. This isn't a continuation of this chain of equalities. I'm just writing something that follows from this. It's going to be a times s squared plus 2s plus 5. Sorry, these coefficients are b and c. Then we're going to have b times s plus 1 squared. Plus c times s plus 1. And this is all over the common denominator. And I can rewrite this as, well, if I look at the s squared term, I have a plus b s squared. Then I have 2a plus 2b plus c. Uh, 2b. S, and then I have 5a plus b plus c. And what that gives me is a system of equations, and we know how to solve systems of equations. So I'm going to write the s squared coefficient. And if I look at the s squared coefficient, I have a, b, 0c. Then I have 2a, 2b, c. Then I have 5a, b, c. And what I have is that if I sort of put A, B, and C here, then this should give me 1 because there's a 1 in front of the s squared, and then these are zeros. So if there's one thing that you learned in this course, it's how to do row reduction. Now, I'm going to subtract from here. So I'm going to get 1, 1, 0. Then I'm going to get 0, 0, 1. Then I'm going to get 0. Then I'm subtracting 5 from here. So I'm going to get -4 here. And then 1, because that's not affected. Then I have 1. Then I subtracted 2 of this. And then I subtracted 5 of this. So now I'm going to clear up this entry. I guess that's the only thing that I'm going to do. I may as well also rearrange the rows. Okay, so if I take this -4 row, I'm going to rearrange it. And I subtract 1 from here. Then I'm adding 2 to here, so I'm going to get -3. And then this row I'll keep as is. Then okay, this is a bit different from how I did the calculation in my notes, but let's just check that, do it and just check that I don't get any typos. So if I add this equation divided by 4, then I get subtract 1 here and I subtract 3/4 here. So I'm going to get 1/4. Then if I look at this equation, I'm just going to divide by -4. And get 3/4. And then here, I already have it. This is actually a bit easier than how I did it in my notes. -2. So what that tells me is that if I look at my original equation, then that's equal to 1/4 times s plus 1. Then we get b, which is 3/4. Times s plus 1 over s plus 1 squared plus 4. And then I have -2. However, I have a 4 here. And I would like to have a 2 up top. That's nice. I'm not going to take out the 2 up front because okay, so this is the Laplace transform of y. And so y is equal to the inverse Laplace transform of the Laplace transform of y. And we basically start writing it out. So I get 1/4. What does this term give me?
E to the minus x.
T is our variable. So we are taking an inverse Laplace transform, so S is changed to T's. But conventionally. Now here, we're going to transform it at first, right? So when we transform it, what's it going to give us as a prefactor?
Cos s plus 1.
No.
S-
How we do it is we first, if we have Laplace transform inverse of something like s plus 1 over s squared plus 1 plus 4, s plus 1 squared plus 4, then the first thing that we do is, remember, we write e to the minus t, and then we change the variables. So we're going to get to an e to the minus t here again, and then what are we going to get?
Now it's cosine 2s. T.
Yeah, t, cos 2t. Then here we're going to do the transform again. So minus e to the minus t, and then we have 2 over s squared plus 4, and what does that give us? So 2 is the
Sine
square root of 4. Go ahead.
Oh, the sine 2t.
Yeah. So that's why I kept the 2 up top there. And so by using the Laplace transform, we're therefore able to find a particular solution to this differential equation when given these initial conditions. And I suggested yesterday that when the initial conditions are given at one point with derivatives up to n minus 1 for n the order of the equation, then we're going to get a unique solution. And we do get a unique solution. It's this. So with the Laplace transform won't actually help you solve the previous homework assignments because I want general solutions. And you sort of can't do partial fractions decompositions if you have unknowns because the numbers matter when you're doing partial fractions. But you're going to see that we can actually use the Laplace transform to solve a lot of things. And let's just go back to lecture 10 and let's look at the other problem that we solved. We also looked at the problem of did I just not do it? I just didn't do it. Okay, so we're going to solve a differential equation from scratch then. So wait, did I seriously not do this? I'm pretty sure I did. Did I just make a mistake when looking at this? Nope, I actually didn't do it. Okay, so we're going to consider a fourth order linear differential equation. And let's say y prime prime, no, y to the fourth. Y the fourth derivative of y minus y is equal to 0. And we're going to give some initial conditions. So this problem, by the way, we could solve because it's homogeneous. We could just solve the characteristic equation and then we get some things. So it's not that bad. But I'm going to solve it with initial conditions using the Laplace transform. And we could have made this inhomogeneous and then it would be much harder to solve. So the conditions are going to be that y0 is 0, y prime of 0 is also 0, and so is y prime prime of 0. Now, if I set y triple prime to be 0, then 0 is a solution of this, and so 0 would in fact be the solution. But I'm going to actually make this be 1. So if we take the Laplace transform of y fourth derivative minus y, then what we're going to get is s to the fourth power, the Laplace transform of y. And then we're going to do successive powers of s down to y triple prime, but all of these are going to be 0. So it's just going to be minus 1 because I plugged in the condition. Minus the Laplace transform of y. And then the Laplace transform of 0 is 0. Because it's linear. So that tells us that we have that s to the fourth minus 1 times L of y is equal to 1, which tells us that the Laplace transform of y is 1 over s to the fourth minus 1. But if we look at the expression 1 over s to the fourth minus 1, then this can be difference of squares. So we get s squared minus 1 and s squared plus 1. So this is a fourth order polynomial, but it's one that's very easy to factor. And then we're going to write that this is a over, I want to do it exactly like I did it here. So let's do s minus 1 plus b over s plus 1. And then it's just s squared. It's not s squared plus anything. So I'm just going to do c s plus d over s squared plus 1. And so what all of that tells me is that a times s plus 1 times s squared plus 1 plus b times s minus 1 times s squared plus 1. Well, let's say 1 is equal to plus cs plus d times s squared minus 1. And then let's just simplify these expressions. So we can see that this is going to be s cubed plus s squared plus s plus 1. So the cross terms don't combine because there's an s squared and there's an s. This is going to be s cubed. Then if we look at the s squared term, it's going to be minus s squared plus s minus 1. And then this entire thing is going to be c s cubed. Then if we look at the s squared term, that's going to be d s squared. Then we're going to get minus CS minus D. And so what that tells us is that this is A plus B plus C times S cubed plus A minus B plus D. S squared plus A plus B minus C. S. And then, okay, there was no way that I'd have enough space. A minus B minus D. Okay, so this is a 4x4 system. So rather starting with the S cubed coefficient, I have 1, 1, 1, 0. Then I have 1, -1. There's no C, so it's 0. 1, 1, 1, minus 1, 0. 1, minus 1, 0, minus 1. And this is equal to, this is the S cubed term, S squared, S, so 0, 0, 0, 1. Good. Okay. Yeah, that's right. Well, let's make all of these entry 0. So I'm subtracting 1 from all of these. Then I'm subtracting 1 from all of these again. And then I'm doing nothing with these. And then there was no entry here. There was a 0, so nothing changes. Okay, well, that's pretty ambitious. I did several steps at once. So I'm going to use this to cancel that out. So I'm subtracting 1. Then I'm subtracting 1/2. Then I'm adding 1/2. Now I'm going to take this and I'm going to divide it by -2. Rather 1/2. Then I'm going to also subtract, add this to this. So, well, actually, so this row is going to stay the same. And let's make this a bit bigger. I may as well make that 1. And then this row, I'm going to add well, subtracts this. So I'm adding 2, I'm adding 1. And then I'm subtracting 1. And then I didn't actually do this row to any other rows. So all of the other things were zeros. So that stays the same. So when I explained it, it was sort of clear how I went from here to here, although if you're reading it, that's several steps at once, so it's harder to read. Now, I feel like just erasing this and replacing this with, you know what? Screw readability later on. Let's also erase this and make this a 1 and minus 1/2. Then we want to get rid of these entries, and it's 1, 1, 0. So like, you know what, screw readability entirely. This only makes sense when you watch it live because these are 0 entries. And then I want to do the appropriate things here. So here I subtracted 1/2, and so here I added 1/4. Here I added 1/2, and so here I subtracted 1/4. This row was fine as it is. And then this row is minus 1/2. So what that tells me is that if I consider this expression, then star is equal to, so A is 1/4, and then I believe that was 1 over s minus 1. Then minus 1/4, 1 over s plus 1. Double check that. Yep. Then C is 0. And then I get minus 1/2. That's D, 1 over s squared plus 1. So what y is equal to is it's the inverse Laplace transform of the Laplace transform of y, which is equal to, and then we can just read it off. So it's 1/4 times what? This is in terms of q.
E to the q.
T, minus 1/4
E to the minus t.
and then minus 1/2
Sine of t.
Okay, so that solves this particular equation. Now we're going to do something really cool. Let's see, what time is it? Okay, we have plenty of time. So let me just show you for 2x2 systems. And so I wrote down an example, but it was actually too terrible to solve. But I will do it in general. So what about Laplace transforms? For systems. So they actually make systems easy. Well, when I say easy, we're about to see that there's a 2x2 system that's not going to be easy. Suppose that you have like a 2x2 system, like x is equal to a x prime plus bx plus f, and y prime is equal to c x plus d y. This should be a y. Plus g, and these are both functions of p.
Oh,
So what we get then is that basically for a is equal to a, b, c, d, and f is equal to f, g. We want a x, x prime is equal to, so that's our usual system. So let's take a Laplace transform of everything in sight. We're going to give it some initial conditions. So this is a first order system. So we'll say that x of 0 is equal to, let's say, x naught, and y of 0 is equal to y naught. Because for Laplace transforms, we need initial conditions. Then what we get is that the Laplace transform, well, let's say s times the Laplace transform of x minus x naught is equal to a times the Laplace transform of x plus b times the Laplace transform of y plus the Laplace transform of f, and then s l y minus y naught is equal to b, so it's going to be c d l g. And if we rearrange this, then what we get is that s minus a L of x minus b L of y is equal to L of f plus x naught. And that's minus c L of x plus s minus d L of y is L of g plus y naught. And in equations, let's say also that basically sort of like I'm going to call this vector x naught is the vector x naught y naught. Then what we get as a result is that s times the identity minus a times the, so now we're going to sort of do the Laplace transform of the vector x. So this is the Laplace transform of x and the Laplace transform of y, is its two components, is equal to the Laplace transform of vector f plus x naught. And that means that we can compute what the Laplace transform of x and y are going to be, what Laplace transforms of x and y are going to be. And that's just going to be SI minus A inverse of L of F. And this applies equally well for any other dimension of system. So this also applies for 3x3 matrices. And so that'll let you solve for the Laplace transform of x and the Laplace transform of y, then you invert them, and then you get the Laplace transform, then you get x and y. So here's an example that I'm not actually going to solve in full. So suppose we have something like x prime is equal to minus 3x plus 4y plus sine t. And y prime is equal to minus 2x plus 3y plus t. And then we have that's x of 0 is equal to 0 and y of 0 is equal to 1. The blue dots do not look good here. Then what we have basically is we can just set up the system like we did before. So it's going to be S, then it's going to be minus A. So it's going to be SI minus A. S plus 3 is going to be the entry here. Minus 4 is going to be the entry here. Plus 2 is going to be the entry here. And then S minus 3 is going to be the entry here. And that's going to equal the Laplace transform of sine t plus this components. Well, sine t gives us, so that's the nicer one. So it's going to be 1 over s squared plus 1. And then t is going to give us 1. So it's n factorial divided by s to the n plus 1. And then we should remember that we also have this y equals 1. So we get that 1 here. Well, what that tells us is that the Laplace transform of x. And right now, this example is looking good and easy. And this is the point at which it stops being good and easy. So we get 1 over the determinant of this. So this is some difference of squares. And then this is going to give us plus 8. Sure. Then what we're going to get is we're going to take this matrix. We are going to swap these entries because that's how we invert 2 by 2 matrices. And then we're going to put negative signs on here. And then, sure, why not combine this? So there is a reason for actually not combining these. Because the first thing that you do when doing partial fractions decompositions is to make the degree of the numerator less than the degree of the denominator. But we're sort of going to divide by something else, and then the degree of the numerator is going to be less than the degree of the denominator. And I'm not going to solve this example fully anyway, so I may as well just say s squared plus 1 over s squared. It's technically better to not combine them, because then you sort of already have part of the partial fractions done. But I'm not going to do the partial fractions here. So this is 1 over s squared minus 1. And then what we're going to get is s minus 3 over s squared plus 1. Then we're going to get plus 4s squared plus 4 over s squared. Then we're going to get minus 2 over s squared plus 1. And then we're going to get, well, I guess I can do the multiplication out. So it's going to be s cubed. Then the s squared term, it's 3s squared. Then for the s term, it's going to be 1. And then for the constant term, it's plus 3. So I'm going to actually bring the common denominator out front.
Wait, isn't it supposed to be s squared minus 9 plus? Oh. Oh, yeah.
Am I good? Okay, good. Squared. Okay. Then here I get s cubed minus 3s squared, and then I need to multiply this by s squared plus 1. So I'm going to get plus 4s to the 4th. Then for the s squared term, I'm going to get 4 plus 4, so it's going to be 8. And then I'm going to get plus 4. Here, I'm going to get minus s 2s squared. And then I'm going to get this term, and then I'm going to basically, okay, let's do a visual aid. So s to the 4th plus 3s cubed plus s squared plus 3s. So that's shifting it over by 1, and then multiplying it by 1, then it's just going to be s cubed plus 3s squared plus s plus 3. So overall, that's going to give me s to the 4th plus 4 s cubed plus 4s squared plus 4s plus 3. And I can rearrange that as 1 over s squared minus 1, s squared plus 1, s squared. Then here I'm going to get 4s to the 4th, then plus s cubed. Then 8 minus 3 is 5. Are there just no s terms? There are just no s terms. Then here I am going to get 1 s to the 4th coming from here. Then there's going to be plus 4s cubed. Well, okay, so these terms are already, it's just the s squared that gets shifted down. Oh, So my notes don't have a 4 coefficient here. I could quickly look at the source material. The source material does not have an S, so where did we go wrong? If we multiply these out, we get 3s here. And then if we multiply this by S squared plus 1. Oh, I see. It's S squared, so actually this shift is different. This changes a 3 to a 5. Yeah, so it's actually S to the 5th. Um, S to the 5th. Plus 3S to the 4th. Plus 2S cubed. Plus 6S squared plus S plus 3. And then we can just copy this expression over again. And the 6 changes to a 4. And this is where I'm going to stop doing the problem. Because then we can partial fractions expand these, but this is a 6th order thing. So we're going to be solving a 6th order system in order to do this partial fractions expansion. And that just does not sound appealing. So then you can do a 6th order, then solve a 6th order system. Well, let's say 2 6th order systems. That does not sound fun. But we're going to see that the Laplace transform is actually useful in occasionally. So it's 6:57. So let's take a break until 7:10. Okay. See you then. Whoops, okay, here we are. So now we're actually going to do some genuinely new stuff in terms of what we were able to solve. So I'm going to consider the following system of equations. It's going to be x double prime, well, that's new, plus y prime, plus 2x is equal to 0, and 2x prime minus y prime is equal to cosine of t. So this is an inhomogeneous linear system, except that it's not a first order because, well, first off, the x's and y's primes are mixed, and then there's a second order x prime prime. So what this actually is it's a second order linear inhomogeneous system. And we haven't discussed how to solve second order systems before. Now I'm also going to give it some initial conditions. The initial conditions are, I'm going to tell you what x naught is, it's 0. Okay, I'm going to do the most boring initial conditions. I'm going to tell you what x prime is because the second derivative appears. It's also 0. And then y, only the first derivative appears. So I'm just going to tell you what y is. It's also going to be 0. So given that we start at the origin, how does the system evolve? Well, what we're going to do is, we don't know how to solve it otherwise, but we do know that we can take the Laplace transform. So taking the Laplace transform gives me s squared times the Laplace transform of x. Then all of these terms are 0. Plus s times the Laplace transform of y. And then plus 2 times the Laplace transform of x. So all of the derivatives just go away. Then we get 2s times the Laplace transform of x minus s times the Laplace transform of y is equal to, cosine is the more annoying one, so it's going to be s over s squared plus 1. Well, we can rearrange this. What we get is that s squared plus 2 times Laplace transform of x plus s times the Laplace transform of y. And then here we get 2s times the Laplace transform of x minus s times the Laplace transform of y is equal to 0, is equal to s over s squared plus 1. And this looks like a linear system. So rewriting it as a linear system, we get s squared plus 2 s 2s minus s. Yeah. So that's equal to 0 and s over s squared plus 1. So as a consequence, L of X and L of Y. Well, that vector is equal to 1 over, then I could say minus S cubed minus 2S minus 2S squared. Then minus S, then minus 2S, then minus S, then S squared plus 2. Cool. So this we can factor as minus 1 over S times S squared plus 2. And then this column doesn't matter because there's a 0 here. So it's just going to be minus S squared over S squared plus 1. And then S times S squared plus 2 over S squared plus 1. Or I can rewrite this as S cubed plus 2S. Okay. And then these S's actually cancel out. So if I just bring everything in, I'm going to get S over S square. Well, I can just factor this. S plus 1 plus 1. S plus 1 squared plus 1. So this isn't bad. It's going to be a 4th order system. Then here we have minus S squared minus 2 over the same denominator. And then we're going to solve the first one. So we can write that as A times S plus 1 plus B over S plus 1 squared plus 1. And then C S plus D over S squared plus 1. And what that tells us, well, before I write what that tells us, I'll just put the usual thing here. And then I'll cross multiply. So I'll get that S is equal to okay. A times S plus 1 times S squared plus 1 is going to be well, there's going to be s cubed plus s squared plus s plus 1 plus b times s squared plus 1 plus c. Well, this expression here is s squared plus 2s plus 2. So s cubed plus 2s squared plus 2s plus d s squared plus 2s plus 2. And so the highest order is s cubed. So we're going to get a plus c s cubed plus a plus b plus 2c plus 2d. Then we're going to get a plus 2c plus 2d. Wait, why did d contribute s? D is s squared, so it's actually ds squared. No, it's 2. And then this is times s. And then we're going to get a plus b, no c, plus 2d. Okay, so if we look at a's contributions, it's 1, 1, 1, 1. If we look at b's contributions, it's 0, 1, 0, 1. If we look at c's contribution, then it's 1, 2, 2, 0, and then this one is 0, 1, 2, 2. So that's right. So in summary, I'm not going to write the bars. We have A, B, C, D. A, B, C, D. A, B, C, D. A, B, C, D. This is s cubed. This is s squared. This is s. This is 1. Okay, let's get rid of the first entries. This, nothing changes here. Now I'm subtracting 1 from all of these. And then I'm doing nothing here. And I'm also doing nothing here. Okay. Let's get rid of this entry. I should be copying these matrices more. Let's get rid of this entry. So I'm subtracting 1. Then I'm subtracting 1. Then I'm subtracting 1. Yeah, I really should be copying these more. Then I'm going to get rid of this entry. So here I'm going to subtract 1 from all of these. Well, subtract 1 from here and subtract 1 from here. Then I'm going to subtract 2 from here. And I'm going to subtract 2 from here. Then I'm going to subtract 1 from here. And I'm going to subtract 1 from here. Then I'm going to add 2 here. And then I'm going to add 4 here. And then I'm going to add 2 here. And okay, screw readability, 5 to 1 2/5. Okay, so I'm subtracting 2. And therefore I'm subtracting 4/5. Now I'm adding 1, and therefore I'm adding 2/5. And now I am going to add 2, and therefore add 4/5. So that wasn't that bad. So what that gives me is, well, here's my ABCD. So -1/5 s plus 1. Then, yeah, B is -3/5. That looks right. That is what I copied down. 1 over s plus 1 squared plus 1. Then 1/5. And that's going to be s over s squared plus 1. And then this is going to be plus 2/5. 1 over s squared plus 1. So that is the Laplace transform of x. Now, I have some good news for you. And that's that I am not going to repeat this for the Laplace transform of y. There's actually a shortcuts. Look at this formula right here. So we have this formula here. So recall. Let's divide everything by s just to clean this up. So I believe there was a 2 here. Let's just see if I'm doing that right. No, the 2 was n here, in fact. So that means that L of y is equal to twice the Laplace transform of x plus 1 over s squared plus 1. And that's already partial fractions expanded. So I don't have to repeat this process again. So I know what the Laplace transform of y is as well. And then I guess I can just copy all of this. And I can multiply this by 2. And then this becomes a 4, but I'm also adding one of them. So this actually becomes a 9. Okay, so that I told you what the Laplace transform of y is, but actually we're sort of getting ahead of ourselves. Because it's good to have the Laplace transform. It's good to say what x is while this is on screen, because otherwise we're going to have to consult back. So therefore, x is equal to, and now we're going to the inverse Laplace transform this. So we're going to get minus 1/5, then e to the negative t. And then it's going to be s over s squared plus 1, which is cosine. Minus 3/5. Then what do I get here?
Sine t.
Yeah, and then I need to remember it's also at this one. And then these are basically the same. So I don't have to.
Did the original equation have x with y in it? So could you use that instead of doing the Lagrange thing?
The original equation. What do you mean? Sorry.
Or like, could you plug in, like, let's say you plugged in, you have a formula for x right now. So let's say you plugged it in the first equation, then you could find y prime, and then you just take an integral. Oh, but you're right, since you already have the
I have the Laplace transform of x.
Right.
So yeah, basically taking the Laplace transform made all of the derivatives go away. At the moment, this is sort of like annoying because this is a second order differential equation. It's a second order system. So I don't think there's anything we can do. Okay, and then y is, so why this was a really big shortcut for finding it. And in general, you should use this shortcut whenever possible. So Yeah, just -2. You know what? I should copy more. We multiplied this by 2. And then this 2 became a 9. So that's a 2, that's a 6. That's a 2, and that's a 9. So there, we solved, this is something genuinely new. We have never before been able to solve a second order linear system, but now we solve a second order linear system for a particular solution. Okay, I'm going to mention one fact and then I'm going to do some examples, and I'm actually not going to prove this fact because I'm going to prove it next time if I find some applications for it. But at the moment, we're not going to use it. But it's actually cool to know. So I'm going to define the convolution of two functions. Evaluated at t to be the integral from 0 to t. And then I need some variable, and s is a bad variable to use. So I'll make the variable be, okay, I'll make the variable be the most annoying thing possible, a Greek xi. Yeah, that was the most annoying possible variable choice to make ever. So what is this? Basically, f, we're going to look at its values from t, when it's 0, then it's t, and then as xi goes from 0 to t, this goes from t to 0, and this goes from 0 to t. So we're going to start basically at opposite endpoints from 0 to t, and then we're going to integrate the product as it goes backwards. And then sort of t is the bound here, and so this is known as the convolution of f and g. And so the theorem is actually pretty cool. That's the Laplace transform of the convolution is the product of the Laplace transforms. So a corollary of this is that if you're taking the inverse Laplace transform of a product of functions, then that's equal to the convolution of the inverse Laplace transforms. So like an integral, which is an antiderivative of a product, is not the product of the antiderivatives. But here, if you take the anti-Laplace transform of a product, then it's this convolved product of the anti-Laplace transforms. So this actually sort of helps with finding Laplace transforms a lot. But you're going to have to be able to solve this integral. But if you know the Laplace transforms of f and g, then you also know the Laplace transform of the product, inverse Laplace transform of the products.
It's
So
like
that's cool.
a homomorphism.
Yes, it is from multiplicative group of functions to functions with respect to convolution. And by the way, some properties of convolution. Convolution is commutative. And it's associative. So you actually do get a group. And then does it have an identity though? Is there a convolutional identity? And that's a good question. Is there a convolutional identity? Maybe it doesn't have an identity. If you convolve with the function 1, then you're just integrating the function. So that's not good. The convolutional identity is distribution. It's a point that has infinite the convolutional identity is not a function. It's a distribution. It's also associative. So it's not a group because there's no identity. And then it's bilinear. But the unit is not a function. Sort of what the unit is that it's going to be, imagine you take a function and then you sort of take a point. So this is 0. And then you take something that's basically 0 everywhere, and then this goes up. And it's so that the total area under the curve is 1. Now take the limits as all of the area concentrates on 1 point. And what the limit looks like is that it's a function that's 0 everywhere. And then it's infinity here. But it's infinity in a way that the area under the curve is exactly 1 at this 1 point. And that's the convolutional identity. And this is a distribution. Known as delta, 0. I guess delta sub 0 to indicate where that happens. But it's not going to be a function. But you can sort of imagine a function that's 0 everywhere except at 0, and it's in like a big enough infinity that's when you integrate, you actually get 1. You can consider it sort of as a limit of functions which just get bigger and shove all of the area here. Okay, well, that was a fun fact. Okay, now I'm going to need to do some examples from the book. So I'm going to do one more example from the book, which I don't have in my notes. I think that on Monday, actually, you know what? Instead of doing examples from the book, let's do a review. That's a better use of time. Because there's a midterm on the weekend, right? So I was going to do more examples of solving linear systems that were not first order using this, but we sort of already did that. So what are you going to be able to do? Well, in general, if you have sort of any higher order system with derivatives of arbitrary order, if it's constant coefficients, and if the inhomogeneous part is good, so polynomials, cosines, sines, exponentials, the stuff that gives us rational functions when we Laplace transform it, then it just becomes a problem in rational functions after you do everything. So therefore, we're able to solve arbitrary order linear systems with the inhomogeneous part being whatever. But we're only able to do this when we have particular values. So this isn't going to give us general solutions. Okay, so someone asked me to actually send out, I didn't send out the email, I'll send out the email today. But there was the question of what's on the exam. So I'm going to tell you what's on the exam. Instead of sending an email, I'll just write it out. So assignment 1 covered first order systems. And sort of what's the general first order system looks like is y prime plus f of x y is equal to g of x. But sometimes we're going to write this differently. So for example, sorry, this is no, this is, never mind, ignore that. That's a linear system. The general first order system looks like y prime is equal to f of xy. And the meaning of this is that at every point a comma b gets a slope f a b, and then we plot all of the slopes, and that gives us a slope fields or a direction fields, a distribution. One distribution is the technical math speak term. And then a solution to this differential equation is an integral curve of a distribution. So it's going to be given by some equation such that the equation is its slope at every point is exactly the provided slope. So solutions are integral curves. Of the distribution. Okay, so a special case of first order systems is separable systems. And this is when y prime is equal to a product of functions f of x, g of y. Or let's actually write it a bit better. Let's write f of x over g of y. Then how do you solve separable systems? Well, you cross multiply. So this is the same as saying that dy over g of y dy is equal to f of x dx. And so that tells you that I guess the general solutions are, and I'll write the constants in one place. And so if you take specific antiderivatives, the general solution looks like this. Now, I often want you to write y as a function of x. And if you want to write y as a function of x, then you often have to take c as being not c, but something like log c. Often take c to be something like log c, or something similar. Because, for example, if you have dy over y, then you're going to get log y, and then your c should be plus c. So if dy over y is equal to f of x dx, then you're going to say that log of y is equal to the integral of f of x dx plus log c. And what that's going to tell you is that y is equal to c times e to the integral of f of x dx. Cool. So that's separable equations. Then we discussed linear equations. And a linear equation looks like y prime plus f of xy equals g of x. And this is, so for the homogeneous case, what you do is that it's a separable equation. So y prime is equal to minus f of x y is separable. So done. Now for the inhomogeneous case, we actually did two different solutions for this, but I'm only going to review one of them. So one of the solutions was to find an integrating factor. But I'm going to review variation of parameters instead of integrating factors, because we're going to review integrating factors later on anyway. And so for the inhomogeneous case, use variation of parameters. So we're going to let's y1 be a solution of the homogeneous problem, which we can find by separation. And then use the ansatz that y is equal to u y1. So this was like pretty new and novel and interesting when we did it. But at this point, we've been doing so much variation of parameters that this is just old. We're used to this by now. And so what happens then is that you do, I'll just write it out. So you get u prime y1 plus u y1 prime plus, well, here we have u f of xy. And then what we want this to equal is g of x. That's the original equation. But if we look sort of at this term, then this is u times y1 prime plus f of xy, and that's 0. So as a corollary, we get that u prime, this unknown parameter, is equal to g of x divided by y1. Well, I guess I don't have to write the x. I'll just write g over y1. And this is just a function of x. So this is separable. Well, it's not just separable, you just integrate it. It's already separated, is what I said. I guess I can make the dependence explicit here. Okay, except for the fact that you aren't allowed to jump to this stage. I want you to on the exam start with the onsets, not this integral. And not this integral. So that solves all first order linear systems. We can solve them is assuming that these integrals are possible. We can solve first order linear systems. It's just as hard a problem as things. Then we had some special cases of first order systems. And I think one of them was the Bernoulli system. And so I'm just going to go back and actually just look at what they were, in fact. It was probably in lecture. So then we had the method of integrating factors, and you can also do this. But it actually, it followed, I'm just going to review variation of parameters. I've already reviewed variation of parameters. So Bernoulli equations are, we have a y to the n here. And yeah. So the first method of solving Bernoulli equations is actually not the good method. The second method is actually great, just using variation of parameters. So the Bernoulli equation is except I don't know how to spell Bernoulli. Oulli. So there was one method with substitution, but that's not actually the method that you should use. The method is basically the same as the linear equation. So if you have y prime plus f of x, y is equal to g of x times y to the power of, let's say, alpha. And then you just solve the homogeneous equation. And use the same onsets. That y is equal to uy1, and this works. So that's the easier way to solve Bernoulli equations. We did substitution method, but you don't actually have to do that. And oh, the next thing that we did is homogeneous equations, which are different from linear homogeneous equations. And so this is an equation of the form y prime is equal to some function of x over y, or y over x equivalently. And basically what you do is you use the ansatz, u is equal to x over y, or u is equal to y over x. One of these might make the problem easier. And this actually happened in homework. I don't remember which version I used. These might lead to different integrals. And basically what happens then is that, well, in the first case, if using u equals x over y, equivalently, x is equal to uy. Well, you know what? I'm going to use the other ansatz. I'm going to use u is equal to y over x. So y is equal to ux. And then I'm going to put y over x here. Let's do it like this. So u, then if we calculate y prime, it's u prime x plus u x is equal to phi of u. Well, then I guess u prime is equal to phi of u minus u over x, which equivalently rearranges to du over phi of u minus u is equal to dx over x, and this so separable. Okay, so that's a homogeneous equation. Now for other equations, in general, and so now we're going to talk about exact equations. So the equation y prime is equal to f of x y rearranges to saying something like dy minus f of xy dx is equal to 0. But then you can also multiply this by any other function. So long as it's not everywhere 0. So we will consider equations of the form, let's say f of xy dx plus g of xy dy is equal to 0. However, we'll actually not use f and g. I think the traditional thing is to refer to these as m and n. Now, if we will recall, that's the total derivative of a function is defined to be the partial derivative. I'll write f sub x dx plus f sub y dy, where fx is the partial derivative of f with respect to x. And so if the equation df equals 0 has solutions fxy equals c. So if now when is f when is m dx plus n dy exact? Assuming that this is defined on this rectangle. In other words, when is it locally exact? And the answer is when m of y is equal to n of x. And then if this happens, we covered how we actually find the things. And so there was a bit of an involved process, and I'll probably have to look back at the notes, although it's 8:07. So I can review how to do that and we can take a break. Okay, this review is actually less exciting than I thought, but someone asked for a list of topics, so I should highlight these in blue. I was using blue before. Okay, let's take a break for resume at 8:20. Okay, so let's continue here. So then how do you solve an exact differential equation? Well, first you have to check that it's exact. Then suppose this holds. Then wants f with fx equals m, fy equals n. And so the observation is that if we sort of consider the function vx y is equal to the integral of m with respect to s for this fixed value of y that we find here, ds. And we're going to take a specific antiderivative. Just to make it, I guess, rigorous, we're going to put bounds on this. So where's the x dependence? The x dependence is sort of x is the upper bound for some fixed x naughts. Observation this for this f minus v, if we take the partial derivative of this with respect to x, then that's equal to 0, which implies that basically f is equal to this integral. Plus some function entirely of y. Well, then what's the unknown function of y? Then f y, which is equal to, well, let's say partial y v plus v prime of y. This lets you solve for phi prime of y, then integrates. Then plug back in. To get f. And we don't care about constants because we care about finding one particular f. And then if we find one particular f, then we just write the general solution is fxy equals c. So we added in the constant at the end. So what if our equation is not exact? If m, so then we are going to talk about integrating factors. So if m dx plus n dy equals 0 is not exact, we will try to make mu, this is a mu, m dx plus mu n dy equals 0 exact. And so then there was a general process for finding these. Then we had cases. And we covered the following 3 cases. We covered the case that nx minus my divided by negative n was a function of x alone. We covered the case when nx minus my over m was a function of y alone. And we also covered the case when nx minus my divided by xm minus yn was a function of the product of x and y. And then in these cases, there is an integral that you solve to get the integrating factor. And then when you have the integrating factor, you're not done yet. When you have the integrating factor, you have an exact equation, then you solve the exact equation. And so that covers the first order theory. Then we talked about second order theory. And the main thing that we like in second order theory or higher order theory is when equations are linear. So a linear second order equation is of the form y prime prime plus f y prime plus g y is equal to h. And it's homogeneous if h is 0. So the thing basically is that for the homogeneous case, with constant coefficients, so in general, actually, this applies to nth order equations. So for a nth order equation, of the form, let's say a sub n y to the n plus dot dot dots plus a1 y prime plus a naught y is equal to 0. So this is a general nth order constant coefficients differential equation. We're going to use the ansatz that y is equal to e to the let's say t x. It's confusing because now t is a parameter. So you know what, I'll say e to the lambda x. And what happens is that with this ansatz, the equation becomes a to the n lambda to the n plus dot dot dots plus a naught times e to the lambda x is equal to 0, implies that y is a solution, y equals e to the lambda x is a solution exactly when lambda is a root of the characteristic equation. Associated to this thing. Now for repeated roots, as this you have that basically x e to the lambda x upwards to x. Well, you know what, I'll write f for a mth order roots. We have that's e, so the mth order root lambda, e to the lambda x is a solution. e to the x times lambda x is a solution, all the way up to x to the m minus first power. So you want m solutions in general, and if it's a repeated root, you just keep adding powers of x. So that tells you how to solve arbitrary degree, not just second order, but arbitrary order homogeneous equations with constant coefficients that are linear. Now, so the constant coefficient case is great. But now we talked about the Wronskian. And so if you have, I guess, two equations, the Wronskian of y1, y2 is the determinant of y1, y2, y1 prime, y2 prime. And we saw that if we have a linear equation that's homogeneous, but not necessarily constant coefficients, so for second order equations, then we can use the Wronskian to find a complementary solution. Yeah, let's say is a non-zero. Then we can find y2 such that the general solution is cy1 plus cy2. So I'm not going to review how we did that, but I'm just going to remind you that I will put a problem with Wronskians on the exam for finding how to find complementary solutions. Okay, what have I not said this entire time? It's sort of implicit. If you have any linear equation and it's homogeneous, then the space of solutions is a vector space. So if you find particular solution, the general solution is a linear combination of particular solutions, right? So I basically remember that linearity is a thing. So for homogeneous linear equations, gets a space of solutions. Sorry, get a vector space of solutions. And in the inhomogeneous case, you get an affine space. Which means that there's a particular solution, and then you add all of the homogeneous solutions in order to get the general solution. Okay, so now we know how to solve basically the homogeneous case. So the homogeneous case with constant coefficients of arbitrary degree is easy. But if it's not constant coefficients, then you're sort of sad, unless there you know one solution, except that there's another case, and that's an Euler equation. That's the other case in which we're able to do this, and we can do this sort of arbitrary degree. So the arbitrary degree version of the Euler equation is if you have a n x to the n, y n, plus, well, I'll write out the second term, x a sub n minus 1, x to the n minus 1, y sub n minus 1, plus dot dot dots plus a naught y is equal to 0. So what happens is that you took a basically constant coefficient equation that was linear, and you modified it by adding a power of x to the n to every single coefficient. So now it's no longer a constant coefficient equation. And basically a substitution works here. C notes. Not going to discuss this. Okay, so this is the theory of solving linear higher ordered equations. Homogeneous, great. Euler, great. Not one of those cases. Well, you better know one of the solutions, and then you can use the Wronskian to get the other, but we can't say anything more in the general case. Then there was the question of, well, how do we solve the inhomogeneous equation? And this was variation of parameters. So variation of parameters. And so what happens? What time is it? It's still okay. So 12 minutes. I'm basically going to review linear systems, not that much because it's fresh in memory. I'm reviewing all of the previous stuff, and then I'll just write what the topics were for linear systems. So variation of parameters was for second order systems. So let's y1 and y2 be linearly independent solutions of the homogeneous equation. Then use the ansatz that y is equal to u1 y1 plus u2 y2 when solving the inhomogeneous equation y prime prime plus f y prime plus g y is equal to h. And what happens when you do this is that you have basically 2 degrees of freedom and one equation constraining them, so you can add another equation constraining them. So you add the equation that's u prime y plus 1 plus u prime y2 is equal to 0. And then you get the equation that's u prime y1 prime plus u prime y2 prime is equal to h. So that's how it works out. And this is a system of equations for u. For u prime. Sorry, this is u1, u2. For u1 prime, comma u2 prime. And then you invert it. So solve it, solve gets u1, u2 by integrating. And then plug in. So if you're able to solve the homogeneous system, then variation of parameters lets you do it. And then I also reviewed a variation of parameters was for third order systems last lecture. See lecture 10 notes. Actually, I think it was lecture 9. Was it lecture 9 or 10 that I spoke about this? I think last time was all Laplace equations, so it was lecture 9. Okay, so that covers basically the theory of, I call it the second order theory, but I really generalized it to sort of higher order things, and I will put higher order things on the midterm. I'll only do variation of parameters up to third order. I won't do higher order variation of parameters. And then finally, we get to all of the content about linear systems. And basically, the thing about linear systems is that we're really going to focus on constant coefficients, first order systems.
Oh, there's also the undetermined coefficients.
Yeah, that's true. There was also a method of undetermined coefficients. Fine, good point. This is an alternative to variation of parameters. So the point is basically if the inhomogeneous part so I didn't develop this fully. In general, it'll let you do the inhomogeneous part for the type of things that we were able to solve with inverse operators. If the inhomogeneous part is an exponential or sine and cosine, or actually a polynomial times an exponential or sine or cosine, then you can also do that. If the inhomogeneous part is let's say let's say like a e to the lambda x, or cos a cos let's say bx, then there is a shortcut method. Instead of using variation of parameters. C notes. You can do variation of parameters even if this is sort of multiplied by x to the n. But I didn't cover how to deal with that. Sorry, undetermined coefficients in that case. Okay, so linear systems. So constant coefficient first order systems look like x vector prime is equal to a x plus f. And then for the homogeneous case, which we spent a lot of time solving, basically the short form of it was that we use the ansatz that x was equal to some unknown vector times e to the lambda t. And then we got that this is a solution if and only if v is an eigenvector of a with eigenvalue lambda. So that's when this happens. But what happens in general if there's a repeated roots? But what about when? Okay, so how do I find the eigenvalues? So first, I find the eigenvalues by solving determinants of a minus lambda I is equal to 0. And this is a nth order polynomial in lambda. Cool. So then for every eigenvalue, there's going to be at least one eigenvector. But what if an eigenvalue has higher multiplicity? In other words, it's a root of this equation with higher multiplicity. So for every distinct eigenvector, eigenvalue, get at least one eigenvector, non-zero eigenvector. But for repeated roots, it becomes more complicated because maybe you can find multiple linearly independent eigenvectors, or maybe you can't. And then you have to use a more clever ansatz. So for repeated roots, you in general get something of the following form. So you might have some eigen vectors, like v1, which gets sent by a minus lambda I. I'll write that in blue for diversity. That sends that to 0. But then you might have things where it's sort of a degenerate eigenspace and there's no second eigenvalue, but there's a vector v2 that gets sent by a minus lambda I here. And this might continue for some orders. And in this case, we have a special ansatz. And so C notes. But in general, summary gets n solutions. You can always find n linearly independent solutions. So yeah, we just did that recently. I'm not going to cover all the details, but you do a bunch of linear algebra. And by the way, one thing that I haven't talked about in this entire review is what do you do if there are complex roots? So for example, in this case, for second order equations, you have to make this real if it's complex. So if it's complex, make it real. Make real solutions. C notes. So that's a bit involved, but I'm just going to gloss over that. And then what about inhomogeneous systems? Let's see, how am I for time? Oh, I actually have 10 minutes. I don't think I'm going to use the 10 minutes. I'm not going to say that much. So for inhomogeneous systems, well, you should know n linearly independent solutions to the homogeneous system. Given linearly independent solutions, y1 through yn, of the homogeneous system, and these are vectors. You can construct the fundamental matrix of the system. It's a matrix whose columns are the solutions. And then what happens is that you can do variation of parameters. So how do you do variation of parameters? Then do variation of parameters. And you'll have to invert X. Along the way. Again, C notes. And then we talked about matrix exponentials, but I'm not actually going to put any questions about matrix exponentials on the exam. So technically, matrix exponentials give you a way of solving in homogeneous systems by just calculating the matrix exponential for constant coefficient ones. Sorry, for homogeneous constant coefficient systems. But it's finding what the matrix exponential isn't really any easier than the process that we did right here. And so with respect to that, that's the material on the midterm. So we're not going to put operators or Laplace transforms on the midterm, but end of examinable midterm material. Did I miss anything? I think that's all. So I went over systems very briefly, but that's only because there's a lot to say and we just did it recently, so I'm not going to say everything again. So that is what's on the exam, and so I don't have to write a list of topics, I just have to send you this. Okay, good luck with that. I'll send that out on noon on Saturday. And then the homework is due on Tuesday so that you have a bit of time to finish it after the exam. I didn't want both things to be due at the same time. And then homework 3 will be posted after that. And I think that really we might only have 3 homeworks, or I might just do a 4th short homework. Because I do, okay, on Monday, if I have time, I am going to do what is actually the most troll lecture ever. I'm going to start doing applications, but I'm going to do like very amusing applications. So I think that maybe I can do 3 hours of circuit analysis. Literally, just that's going to be the lecture. That's going to be the applications. There's going to be like resistors, there's going to be induction coils, and there's going to be other stuff. And then we're going to see how the voltage in the system evolves over time. Okay, so I think that's that. See you on Monday and good luck.